An important concept is that of an orthogonal projection of a vector onto another vector. So given a vector u, we want to decompose a vector y into the sum of two vectors so that one of them is a multiple of u and the other one's orthogonal to u. Okay, so we'll start with the vector u. Okay, we're trying to decompose a vector y that's given into the sum of two vectors where one of them's a multiple of u. If it's a multiple of u, then that means it's going in the same direction as u. It's just parallel, which is the same direction as u, meaning it's a multiple of u. So okay, so this will be the vector y hat that we're referring to. That's the vector that will be part of the sum that's in the direction of u. And now the direction orthogonal to u, so this vector would be orthogonal to u. Okay, so we'll call this as our z. Okay, so if you remember how to add vectors, this vector plus this vector is equal to this vector. Okay, but this vector z, it doesn't matter if I place it here or if I place it over here. Okay, so what this shows me then that is that the y hat plus the z will be equal to y. Okay, this y hat, because it's in the same direction as u, is some multiple of u. So I'm going to rewrite y hat as some multiple, I'll just call it alpha, times the u. Okay, so I want to find out, how do I find that projection, that y hat, that is the projection of y onto the vector u? Well, I know that I want y to be y hat plus the z, which means that the y minus the y hat will be the z. So once I find the y hat, I get the z simply by taking y minus the y hat. Okay, but this vector is supposed to be orthogonal to u. Okay, so I know since z dotted with u is orthogonal, so z and u are orthogonal, so their dot product is 0. That means that that's the same thing as y minus y hat dotted with u. But remember, our y hat's in the same direction as u, so that's equivalent to y minus alpha times u dotted with u. Well, distributing this dot product, I've got y dotted with u minus alpha times u dotted with u. That means that alpha times u dotted with u is just y dotted with u, which means that the alpha then is just y dot u over u dot u. Okay, so if I'm trying to find y hat then, which is the projection of y onto u, which is, they're just saying L is the line passing through u, so they're just calling that L. That's just going to equal to the alpha. Right, we're saying that y hat was alpha times u. Here's our alpha dotted with the vector u, or times u, because that's not a vector. Okay, so that's how we'll find what the y hat is, and once we get the y hat, we'll just simply find the z by taking y minus the y hat. So y minus that y dot u over u dot u times u. Okay, so this is called the projection of y onto u, or the line containing u. Okay, so I've got two vectors, y and u, and I want to find the projection of y onto u first. Okay, so the projection of y onto u, we'll just call that y hat, is y dotted with u over u dotted with u. Well, y dotted with u will be 28 plus 12. U dotted with itself will be 16 plus 4. So that's 40 over 20, which is just equal to 2. Okay, so that's the y hat. Okay, now that's not the y hat. That is the projection, which is just the dot product. So I need to have this times u to get the projection. So 2u is the projection. Okay, so the y hat is actually the vector, okay? And then the 2 is the multiple of that vector that would be the y. Okay, so now I want to write y is the sum of two orthogonal vectors, one that's in the span of u, which this one's in the span of u. So now we want to find one orthogonal to it. Well, we know that y is equal to y hat plus some z vector. Z then will just be equal to y minus y hat. So z, which will be the one orthogonal to u, will be 7, 6 minus y hat. Now y hat was twice u, which if I took this one step further, that's just going to be 8, 4. I'm just taking twice the vector u, which comes out to be -1, 2. So that's the vector u, z. And let's just check to make sure. Is y equal to y hat, which is 8, 4, plus -1, 2. Yes. Okay. This comes out to be 7, 6. Okay, so we know that they do sum up. Are those two vectors orthogonal to each other? So I just want to check. Is z dotted with u hat equal to 0? Well, that's 8, 4 dotted. So it's real simple to check these. Just check the dot product of the two answers that you get, and you do get that that comes out to be 0. Okay, so let's see what you've actually found geometrically, since we can draw this one. 7, 6. 1, 2. So here's the vector 7, 6. So there's y. U is the vector 4, 2, which is right here. Okay, so we wanted a multiple of u, which we got 8, 4 to be that multiple of u. Okay, so we projected y onto this vector, and then the other vector, the what was it, -1, 2, should just be this vector moved to the origin. -1, 2 would be right here. So here's our two vectors. Here's the y hat, here's the z, and you see that the sum of those two vectors does equal to the vector y. Okay, now I want to find the distance in this figure. Okay, so this is just showing the picture that we just found. I want the distance from y to the line L. So L is just that span of it's the line that's going through u. So it's the span of the vector u. I want the distance from y to the line, which would be this distance right here. Okay, well, that distance is just the length of that vector, which is the vector z. Okay, so that distance is just going to be the magnitude of z. If you want to look at it as if you're working with the points, the vector y is the vector 7, 6, and the vector y hat was 8, 4. The distance between those two would be the square root of 1 squared plus 2 squared. But notice that that's just the magnitude of z. Okay, so if you just take the distance, if you want the distance to that line, which is the span of the first vector that you're projecting onto, it's just going to be the magnitude of that orthogonal vector. Okay, so now let's look geometrically what we've just done. We're looking at the subspace spanned by u1 and u2. where U1 and U2 are orthogonal. So we've got our U1 going here, and we've got our U2 going in this direction. Okay, so we're just looking at orthogonal basis here. If you take any y, it can be written in terms of those two vectors. Okay, and those weights for each one of those two vectors is just getting a vector in the direction of those. So if you find the projection of y onto U1, it will actually be, that projection will actually be this vector right here. Okay, that vector is just this. So this is just y projected onto U1. If you found then the projection of y onto U2, so come over here, this is the projection of the y onto U2. So that would be y2 hat, and this other one was the y1 hat. So all we're doing is we're projecting the vector y, which is here, onto each of the basis vectors, the ones that this orthogonal projection, and you'll see that this is the exact same thing that we found earlier. If we were trying to write it as a linear combination of two vectors that were in an orthogonal basis, those weights are just the vector y projected onto, onto U1, which is y dot U1 over U1 dot U1, or the vector y projected onto U2, which is the y dot U2 over U2 dot U2 times the U2. So these are just the projections onto each of those two vectors in that set, the basis, in that orthogonal set. Okay, so now why would you care to do this? Well, a lot of physics applications are working with forces. And so there might be some force that's applied in a certain direction, such as this, by being, the car being towed. Well, a lot of times there's a certain direction that you're interested in. So in this case, the direction we're mainly interested in is, the horizontal direction, which is the direction of movement. So we may be more interested in that direction than we are the direction that force is applied to. But we can always take this vector, if we call this one y, we can take the projection of y onto u, which has given us the force, the amount of that force that's causing a movement in that horizontal direction, which is the direction that the cars are traveling. And then we can write the y as a projection onto u plus some vector that's orthogonal to it. Okay, so that's one of the reasons that this decomposition of a force into those orthogonal components is so important. So there's going to be some direction that's important to the problem, and so you'll project onto that and then find that other orthogonal projection.